In this lesson, you will learn about continuity and one-sided limits. Part 1 is notation for one-sided limits and existence of a limit. So first, let's learn about approaching an x value from one side. This notation, where you see this little negative sign, where normally you would expect to see an exponent, that means x approaches c from the left. So if we were to look at a number line, then the x value comes in from the left-hand side of c, and it gets infinitely close to c through numbers that are less than c. Now this notation here, when it has a plus sign up in the exponent position, that means x approaches c from the right. So the x values are coming in towards c, and they're getting infinitely close to c through numbers that are greater than c. They're getting closer and closer and closer to c, but they're all a little bit bigger than c. So remember, this notation means x approaches c from the left, coming in this way, and this notation means x approaches c from the right, coming in this way. Next up, we have one-sided limits. So this notation here means the limit of f of x as x approaches c from the left. Now what this tells you to do is find the y value the function is approaching as the x value approaches c from the left. Similarly, this notation here means the limit of f of x as x approaches c from the right. And that tells you to find the y value the function is approaching as the x value approaches c from the right. Let's take a look at an example and see how this works. Here, we have to evaluate each one-sided limit. We are given this graph of f of x, and first up, we have to find the limit as x approaches 3 from the left of f of x. Now make sure you understand, this is not negative 3. The negative sign is not in front of the 3. The negative sign is up above in the position of the exponent. So this means we're finding the limit as x approaches 3 from the left. And you can see that as x is getting closer and closer to 3 from the left, the y value is getting closer and closer to 1. So we say that the limit as x approaches 3 from the left of f of x is equal to 1. Here we have to find the limit as x approaches 3 from the right of f of x. As the x value gets closer and closer to 3 from the right, the y value is getting closer and closer to 2. So we say that the limit as x approaches 3 from the right of f of x is equal to 2. And remember, these are one-sided limits. We know they're one-sided because of this notation where we either have a negative sign or a positive sign up in the exponent position. And these limits only look at one side, meaning you're either approaching from the left or you're approaching from the right. And it's okay that they came out to be different values. Sometimes they're the same, sometimes they don't exist, sometimes they're different values. Next up, we have the existence of a limit. The limit as x approaches c of f of x equals L exists if and only if the limit as x approaches c from the left of f of x is equal to L, and the limit as x approaches c from the right of f of x also equals L. Another way we can say that is that the limit from the left has to equal the limit from the right. As long as the limit coming in from the left approaches the same value as the limit coming in from the right, then we say this two-sided limit exists and is equal to that value. So this notation, limit as x approaches c, automatically means coming from both sides, left and right. In this example, find each value using the graph at the right. Here we are given g of x. First up, we have to find g of 5. So looking at the graph, we go to x equals 5, go up to the function, and we see that that equals 4. Now we have to find the limit as x approaches 5 from the left of g of x. So as x comes into 5 from the left, we see that the y value is approaching 4. Here we have to find the limit as x approaches 5 from the right of g of x. As x gets closer to 5 from the right, the y value is getting closer and closer to 4. Now because the limit from the left and the limit from the right are equal to each other, then that means this two-sided limit as x approaches 5 of g of x is also going to exist and will equal 4. Now go ahead and pause the video and try this one on your own, then restart when you're ready to check your answers. Here we have to find g of 10, so we go to x equals 10, and we go up, and there's a point here, so g of 10 is equal to 3. Next, we have to find the limit as x approaches 10 from the left of g of x. As x comes into 10 from the left, we are coming along this part of the function, so the y value is approaching 3. The limit as x approaches 10 from the right of g of x means we would be coming along this part of the function, and that y value is approaching 2. Now because the limit from the left and the limit from the right do not equal each other, then we have to say that this two-sided limit as x approaches 10 of g of x does not exist. Next up, I want you to pause the video and try finding all these values, then restart when you're ready to check. G of 15, there's an open circle here and an open circle here, so g of 15 does not exist. Limit as x approaches 15 from the left of g of x means we're coming in here to y equals 0. So that limit equals 0. The limit as x approaches 15 from the right of g of x means we would be coming along this part of the function, which is approaching a y value of -2. And once again, because the limit from the left does not equal the limit from the right, then we have to say the limit as x approaches 15 of g of x, which is a two-sided limit, does not exist. Next, we learn a notation for tiny positive or negative numbers. 0 plus indicates a value infinitely close to 0 approaching from the right. so think of it as a tiny positive number. Remember, approaching from the right means you're coming in through numbers slightly larger than the value, so 0 plus, if we're slightly larger, will be a tiny positive. 0 minus, then, indicates a value infinitely close to 0 approaching from the left, which means slightly smaller than the given number, so think of it as a tiny negative number. And when we say tiny, we mean small in magnitude, very close to 0, but coming in through negative numbers. In this example, evaluate each limit. Here we have to find the limit as x approaches 7 from the left of square root of the quantity x minus 7. Now, because we're approaching 7 from the left, that means we're coming in from this side. And what you can think of it in your mind is 6.9999. You're getting infinitely close to 7 through numbers that are smaller than 7 because you're coming in from the left. Well, if we were to take 6.9999 and subtract 7, we would get a tiny little negative number. So we can write this as the square root of 0 minus. And just to be extra clear here, we don't actually plug in the exact value 6.9999. We don't know what the x value is. We just know that it's infinitely close to 7 coming in from the left. So in our minds, we can use an example of 6.9999, put that in for x temporarily, subtract 7 to discover we would get a tiny negative number. The 6.9999 is something we temporarily use just to help think our way through. Now, of course, you can't take the square root of a negative, so that means this value does not exist. Now, compare that to the limit as x approaches 7 from the right of the square root of the quantity x minus 7. Now, this time, since we're approaching 7 from the right, we are coming in this way. And what we want to think is 7.00001, infinitely close to 7 through numbers slightly bigger than 7. So if we subtract 7 from our number that's infinitely close to 7, but coming in from the right, we are going to get the square root of a tiny positive number. Now that's okay to do. We can take the square root of a tiny positive, and so as x gets closer and closer and closer to 7, x minus 7 is going to get closer and closer and closer to 0, coming through positive numbers, so this will equal 0. So in this case, the limit from the left did not exist because we ended up with a tiny, tiny negative number, but the limit from the right did exist and is equal to 0. Now if we evaluate the two-sided limit as x approaches 7 of the square root of the quantity x minus 7, we have to say that this limit does not exist. And that's because the limit as x approaches 7 from the left of radical x minus 7 was not equal to the limit as x approaches 7 from the right of square root of x minus 7. Remember, for the two-sided limit to exist, the limit from the left and the limit from the right have to be equal to each other, and these two were not. That's why we say the two-sided limit does not exist. Part 2 is definition of continuity. First, let's learn about continuity at a point. So that means we're talking about a function being continuous at one specific point on the graph. F of x is continuous at c if all three of these conditions are met. First, f of c exists, and that means if you plug in x equals c, it puts out a y value. It's not a DNE at that point. Second, the limit as x approaches c of f of x exists. And once again, that means when you evaluate the limit, it outputs a real number value, not a DNE. And third, the limit as x approaches c of f of x has to equal f of c. So what this is saying is that the value you get in step 1, which is f of c, has to equal the value you get in step 2, which is the limit value. So if all three of those happen, then we say that f of x is continuous at that x value of c. Now be sure to note that if any condition fails, then f has a discontinuity at c, which means that it's not continuous at c. Now that we know how to check continuity at a single point, we can talk about continuity on an open interval. A function is continuous on an open interval from a to b if it is continuous at every point on the interval. So that means at every point on the interval, all three of those conditions have to be met. A function that is continuous on the interval from negative infinity to positive infinity, we say is continuous everywhere. In this example, use the definition of continuity to explain why f of x is continuous at x equals 4. So we are talking about a single point here. So that means we have to show that all three of those conditions are satisfied at x equals 4, and then we can conclude that f is continuous at 4. So now we walk through the 3 steps. First up, we have to look at f of 4. And coming over to the graph at x equals 4, we see that it outputs a value of 3. So that means that f of 4 exists. It didn't work out to be a DNE. So we've satisfied step 1. For step 2, we have to look at the limit as x approaches 4 of f of x. Now remember that this is a two-sided limit. So as we come into 4 from the left, we see that the y value is approaching 3. As we come into 4 from the right, the y value is also approaching 3. So this limit equals 3, which means it also exists. And now we've satisfied step 2. And then in step 3, we have to show that the limit value is equal to the function value. And since they both equal 3, we can say that they are equal to each other. So the limit as x approaches 4 of f of x turned out to equal f of 4. Now, because all three of those conditions were met, we know that f will be continuous at 4. So what we can say then is by 1, 2, and 3, f is continuous at x equals 4. So we had to show that all three steps of the definition were satisfied, which is what we did here, and then we can make our conclusion that f is continuous at that point of x equals 4. Now that we've learned how to prove that f is continuous at a point, we want to learn what to do if it's not continuous at that point, meaning that it has a discontinuity. There are two types of discontinuities. A removable discontinuity occurs when the limit as x approaches c of f of x exists, but is not equal to f of c. F could be made continuous if we redefine f of c equal to the limit value, limit as x goes to c of f of x. Now, a non-removable discontinuity occurs when the limit as x approaches c of f of x does not exist. So you can see that a discontinuity is either removable or it's non-removable, because the condition that makes them happen is exclusive to that type of discontinuity. If there's a discontinuity and the limit exists, it's going to be removable. If there's a discontinuity and the limit does not exist, then it's going to be non-removable. In this example, apply the definition of continuity to explain why the graph has a discontinuity, then name which type it is. So we're looking here at x equals 5, and if we apply the definition of continuity, step 1 says we need to look at f of 5 and see if it exists. According to the graph, f of 5 is equal to 7, so it does exist. So far we have satisfied step 1. Now in step 2, the definition of continuity says we have to look at the limit as x approaches c of f of x. And in this case, if we were to look at the limit as x approaches 5 from the left of f of x, as x comes into 5 here, we see the y value is approaching 4. Whereas the limit as x approaches 5 from the right of f of x, as the x value comes into 5, the y value is getting closer and closer to 7. Now, because the limit from the left of 5 and the limit from the right of 5 are different values, that means the two-sided limit as x approaches 5 of f of x does not exist. Now, when the limit as x approaches c of f of x does not exist, and of course, in our case, c is 5, that tells us that we have a non-removable discontinuity. So we would say f has a non-removable discontinuity at x equals 5. So remember, once you discover that the two-sided limit does not exist, that immediately tells you that you have a non-removable discontinuity at that x value. In this example, apply the definition of continuity to explain why the graph has a discontinuity, then name which type it is. Here is our graph of g of x, and we're going to be looking at x equals 8. Now, the definition of continuity, step 1, tells us we will need to look at g of 8 and decide if it exists or not. And because there's a hole in the graph there, we know that g of 8 does not exist. Now, because we failed step 1, we know that the function has a discontinuity at x equals 8. Now we just have to decide whether it's removable or non-removable. And remember, what determines that is whether the limit exists or the limit does not exist. Now, in step 2 of the definition of continuity, we need to look at the limit as x approaches 8 of g of x. Now, in this case, we can do a two-sided limit because we see that as x approaches 8 from the left, the y value is going to 6. As x approaches 8 from the right, the y value is also going to 6. So this two-sided limit exists and is equal to 6. Because this two-sided limit does exist, but is not equal to g of 8, that means that g has a removable discontinuity, and I'm going to abbreviate both of those words, removable discontinuity at x equals 8. Now, because it's a single point that's causing the discontinuity, that's what makes it a removable discontinuity. So g could be continuous, and I'm going to abbreviate continuous, if g of 8 was redefined so that it equaled the limit as x approaches 8 of g of x, which is equal to 6. So in other words, because this discontinuity is caused by this single point, if we could just redefine that point to equal the limit value, then we would have a function that's continuous at x equals 8. So this right here is where we redefined g of 8 to equal 6. In this example, apply the definition of continuity to explain why the graph has a discontinuity, then name which type it is. We are given a graph of h of x, and we will analyze at x equals 12. Now, according to the definition of continuity, we will first have to decide if h of 12 exists. And we look at the graph, h of 12 is equal to 17. So it does exist. So far, so good. We've passed step 1. Step 2 says we have to look at the limit as x approaches 12 of h of x. And once again, we can do quickly a two-sided limit because we see as x comes into 12 from the left, the function is going to 13, and as x comes into 12 from the right, the function is also going to 13. So this limit is equal to 13, which means it exists. So in terms of the definition of continuity, we have passed step 1 and we have passed step 2. Now, step 3 says that we need the limit value and the function value to be the same. And that's where this graph fails. Because the limit as x approaches 12 of h of x does not equal h of 12. Now that means we know that we have a discontinuity, and now we just have to figure out which type. Now when we have the condition that the limit exists but does not equal the function value, we know that means we will have a removable discontinuity. So h has a removable discontinuity at x equals 12. And anytime we have a removable discontinuity, that's when we have to do the redefining and say that h could be continuous if h of 12 was redefined to be that limit value, which we know is 13. So if we were allowed to redefine this point and move it down here, then we would have that h is continuous at 12. Next, I want to help you understand why polynomial functions are continuous everywhere. We will be referring to the steps in the definition of continuity, so let's bring that up. For any polynomial function, p of x, we know that the domain is negative infinity to positive infinity. At every x equals c, p of c will exist. Since the domain is all real numbers, that means we can plug in every possible value for x and it will result in a y value. That's why we say p of c will exist, and it will exist everywhere. So that satisfies step 1 of the definition of continuity for all real numbers. Using direct substitution, we get that the limit as x approaches c of p of x is equal to p of c. Now, since p of c exists everywhere, that now means that the limit as x approaches c of p of x, which equals p of c, has to exist everywhere. So this tells us that the limit exists, which satisfies step 2, and that it is equal to the function value at every c, which satisfies step 3. So because steps 1, 2, and 3 were all satisfied for every possible x equals c on the entire real number line, that means that polynomial functions are continuous everywhere. Next, we explain why rational functions are continuous on their domains. For any rational function r of x with x equals c in its domain, so we have to be working on the domain of our rational function, then we know that r of c exists, because rational functions, as long as you pick an x in their domain, we can plug that in and get a y value. So this satisfies step 1 of the definition of continuity. Using direct substitution, we get that the limit as x approaches c of r of x is equal to r of c. Now remember, every r of c where c is in the domain exists. So this tells us that the limit exists, which satisfies step 2, and is equal to the function value at every c, which satisfies step 3. Therefore, because steps 1, 2, and 3 were all satisfied in the definition of continuity, this tells us that rational functions are continuous on their domains. Consequently, we analyze rational functions for discontinuities at the x values that are excluded from the domain. And now we'll take a look at some examples to understand how this works. In this example, find any discontinuities and determine which type. Justify your answers with the definition of continuity. We are given f of x is equal to the quantity x squared plus 2x minus 3 over the quantity x minus 1. We recognize that this is a rational function. And we just learned that rational functions are continuous on their domains. Now, in this case, we have to exclude 1 from the domain, so then that means that f is continuous for x on the interval -infinity up to 1, union 1 to infinity, everywhere except x equals 1. Now, we also learned that we look for discontinuities at the x values that are excluded from the domain. So that means we should apply the definition of continuity to x equals 1. So that's where we will look. Now, step 1 means we have to do f of 1. Now, if we plugged 1 into f of x, we know the denominator would become 0, so f of 1 does not exist. So because this failed at step 1, we already know that there's a discontinuity. Now we just have to determine which type. And the type of discontinuity is controlled by whether the limit exists or it does not. So in step 2, we look at the limit as x approaches 1 of x squared plus 2x minus 3 over x minus 1. Now, we learned how to evaluate these limits. If we tried direct substitution, we would have 1 plus 2 is 3. 3 minus 3 is 0. So we would have 0 in the numerator, 0 in the denominator. 0 over 0 is indeterminate, so that tells us we have to do some work here. And the technique we learned is to factor this numerator and see if we can get something to cancel. So this is equal to the limit as x approaches 1. Let's get our fraction bar. The numerator will factor into x plus 3 times x minus 1. And of course we have x minus 1 in the denominator. Now we can cancel the x minus 1 common factors. And this becomes the limit as x approaches 1 of x plus 3. And now we can do direct substitution, and this limit is equal to 4. So the limit does exist, but of course does not equal the function value, which is a DNE. So we know that f has a removable discontinuity at x equals 1. Now, because it's a removable discontinuity, we have to make that statement about how it could be continuous if we redefine it. So f could be continuous if f of 1 were redefined to be that limit value. So if we could take f of 1 and stop it from being a DNE and turn it into this limit value of 4, then we would have a continuous function. In this example, find any discontinuities and determine which type. Justify your answers with the definition of continuity. G of x is equal to 3 over the quantity x plus 2, so we recognize that that is a rational function. Which we know means it will be continuous on its domain. So G is continuous for x on the interval. We just have to exclude -2 from the domain. So the intervals will be -∞ to -2, union -2 to infinity. We know that we look for discontinuities at the x values that are excluded from the domain. So we are going to look at x equals -2. And this is where we will apply the definition of continuity. Step 1, we have to look at g of -2. And we see that that does not exist. So we can either write DNE or we can use the undefined symbol, either one. So immediately, because this failed at step 1, we already know that we have a discontinuity, and now we just have to determine which type of discontinuity we have. That's decided by the limit, so we go on to step 2. We have to do the limit as x approaches -2 of 3 over x plus 2. When we try direct substitution here, this turns into 3 over 0, which of course we know does not exist. Or we can use the undefined symbol, either one. Now, because the limit did not exist, we know that means that G has a non-removable discontinuity at x equals -2. Here we have to find any discontinuities and determine which type. Justify your answers with the definition of continuity. We are given this f of x, which is the quantity x squared minus 1 over the quantity x squared plus 3x minus 4. We recognize that it is a rational function, which means it will be continuous on its domain. Now, to determine its domain, we need to factor this denominator. So let's go ahead and factor both the numerator and the denominator. Get our fraction bar in here. The numerator is easy. It's the difference of two squares. So this will factor into quantity x plus 1 times quantity x minus 1. The denominator is also pretty easy to factor. We see it's going to be quantity x plus 4 times quantity x minus 1. Now, just a quick reminder that you cannot cancel this common factor in the function. We can only do that kind of canceling when we're performing the limit. So because this is an equality, we have to leave all these factors in here, but it helps us to determine the domain. We know that rational functions are continuous on their domains. So because we have a rational function, we know that f is continuous for x values on the interval. Looking at this denominator, we see we have to exclude -4 and +1. So when we write that in interval notation, we say it's the interval from -∞ to -4 union -4 to 1 union 1 to infinity. So x can be anything on the entire number line except for -4 and +1. We know that we will analyze the function for discontinuities at the x values that are excluded from the domain. So let's look at x equals -4. We'll start there and apply the definition of continuity. Step 1 tells us we have to do f of -4. Now, if we plug -4 in, we get 0 in the denominator, so this does not exist. Already now, we know that we have a discontinuity there because the function failed at step 1. Now, the type of discontinuity is determined by the limit. So we go on to step 2, and we do the limit as x approaches -4. And let's go ahead and write the factored form of the function here. We've got x plus 1 times x minus 1 in the numerator over quantity x plus 4 times quantity x minus 1 in the denominator. Now here, within the limit, is where we can cancel out that common factor. So this becomes the limit as x approaches -4 of x plus 1 over x plus 4. Now we try direct substitution. If we put -4 into the numerator, we get -3. And if we put -4 into the denominator, we get 0, and this does not exist. Or we can write undefined. Now, because the limit does not exist, we know that means that f has a non-removable discontinuity at x equals -4. Now remember, there were two x values that were excluded from the domain, so we also have to look at what happens at x equals 1. Now we will need to walk through the same steps there. First, we have to look at f of 1. If we plug 1 into the function, the denominator is 0, so it does not exist there. So once again, we know we have a discontinuity, and now we have to go on to step 2, look at the limit to decide which type of discontinuity. So in step 2, we have limit as x approaches 1. Once again, we will use this factored form. We have x plus 1 times x minus 1 over x plus 4 times x minus 1. And we know within the limit, we can cancel that common factor. So this becomes the limit as x approaches 1 of x plus 1 over x plus 4 . The next thing we try is direct substitution. So if we take the 1, put it into the numerator, we get 2. And plugging 1 into the denominator, we get 5. So this limit does exist. This limit is equal to 2/5. Now, because the limit exists, but is not equal to the function value, we know that f has a removable discontinuity at x equals 1. And anytime you have a removable discontinuity, you have to write that sentence where we redefine the function. So we say f could be continuous if f of 1 was redefined so that it equaled the limit value, which of course is 2/5. So it turned out that this f of x ended up having two different types of discontinuities: a non-removable discontinuity at x equals -4, and a removable discontinuity at x equals 1. And remember, anytime you have a removable discontinuity, you have to write that statement of redefining.